between the two lines. So the result HP is equal to M. I have M from here. From the first, I have L common factor. From the second, I have L theta dot. So this is L squared theta dot. And let's do the cross product. Simply N1 cross N1 is 0, N2 cross N2 is 0. So I have this guy minus that guy. This guy is sine squared theta minus that guy is cosine squared theta. And this is in what direction? It's N1 cross N2, so it's N3 direction. Okay? Very simple expression, it's ML squared theta dot in the N3 direction. Yeah, this is the angular momentum. It's I theta dot, angular momentum. Linear momentum is mass times velocity. Angular momentum is the angular version of it. The mass is replaced by mass moment of inertia, and the linear velocity v is replaced by the angular velocity, right? So this is the mass moment of inertia, ml squared, and this is the what is analogous to velocity, right? This is the angular velocity. I times omega or I times theta. This is the angular momentum. Okay, but this is a rigorous way of doing it. You can memorize I omega or I theta dot, but this is very, very special case. And here is the generic expression. You can do it no matter how complicated the problem is. Any questions so far? So we got almost the left-hand side of our equation. I just need to differentiate it. And I will go to build up the terms in the right-hand side. Yes, please.
Sorry, I still have some questions about the,
Sure.
the coordinates itself. The coordinate itself is end coordinates. They're from the car. So we're only looking from the car.
No. N1 N2 is inertially fixed.
And
Well,
that's
the
the-
problem comes with the description. There are no coordinate frames, and it's your role to select your coordinates. Okay?
Yes.
I selected the coordinates far on the left at an inertially fixed point, and they're gonna be inertially fixed, meaning they would not rotate. They're just x to the right, y upward. Okay? So these, by definition, are inertially fixed frame, and I'm gonna write everything in terms of these N1 and N2.
Yeah, I just wanted to get your definition right here because I didn't.
Yeah.
Yeah.
Any other question, please? Yes.
So when you do R P to M, why don't you include the vector from the origin to P?
This is a very good question because I'm not computing the absolute position of M with respect to the origin. I just need from M or from P to M, right? Yeah, this is a very good point. Any question, please? Okay, so I got, like I said, I got the left-hand side of the equation. Let's go and get the right-hand side of the equation. We just do training. Next, we're gonna have a problem and see the value of doing the linear, the angular momentum version. Because for a point mass, Newtonian mechanics is all about point masses in Euclidean space, in three-dimensional space. For a point mass has 3 degrees of freedom in space, so you need 3 equations to fully analyze the dynamics. Newton's second law already gives you the 3 equations of motion. So this is not new pieces of information, it's alternative. The angular momentum version is an alternative, and you can immediately realize that all what we did is that we crossed the whole Newton's second law with R. Okay? When you cross the left-hand side with R, the linear momentum with R, you get the angular momentum. When you cross the right-hand side, the force with R, you get the moment. So it's not new piece of information, okay? You do this or that. Sometimes it's much easier to deal with the angular momentum. And we're gonna see an example. But now we're just doing some training. How to use the angular momentum concept. Any question about that? Let's construct the other terms in the equation. I need the moment about the point P. Everything is about P, right? Angular momentum about P, moment about P. So I need the moment. What are the acting forces on the mass M? What are the acting forces?
Gravity.
Gravity, very good. This is always the case. mg, and what else? Yeah, please don't neglect that. Call it tension, call it reaction, whatever. Luckily, the tension passes through the point and will not play any role. And this is why sometimes we like to use the angular momentum concept, because it allows forces passing through a point, unknown forces. This is an unknown force, right? So I just got rid of it, okay? Because the moment about P, it's just this guy multiplied by 0 distances, because it passes through the point. So there is no moment coming from the tension, the moment only coming from gravity. And you can just do the resolution here. This is mg sine theta multiplied by the length L, correct? So the moment about P due to the acting forces on the mass M is simply mg sine theta times L as a magnitude. What about the direction? What direction is that? To determine the direction of any force about a point, it's as if this is a square and this is a car. So the car to rotate about this square will go this direction. Okay? This direction is from N2 to N1. Positive is always from 1 to 2. So this is negative and N3. Okay? Any question about that? We got the moment, luckily. It wasn't hard. So we're ready to apply the rule. Any questions so far? Okay, let's do it. Here's the rule. HP dot. Let's get the derivative of HP, the red thing over there. So the red, I'm applying this, okay? Differentiate this with respect to an inertial frame. Luckily, it's already in an inertial frame. So it's ml squared theta double dot in the N3 direction equal. And you can see immediately this is I theta double dot kind of thing, right? Equal, the right hand side is the moment about P. So this is negative mgl sine theta in the N3 direction. Yeah, so this is the I theta double dot equals the moment concept that we have learned in undergrad. But because P is not fixed, I have to add this term. Okay? So minus the position vector from P to M, I already have that, which is L sine theta N1 minus cosine theta N2. And I have M RP double dot, the acceleration of the point B. What is the acceleration of the point B, please?
The car is moving constantly.
The car is moving in the x direction, in the N1 direction. So what is its acceleration? It's moving with a position distance called x of t. What's its acceleration? It's x double dot as a magnitude. And what about the direction? The N1 direction. Okay? This is cross. Okay? Any question about that? Okay, let's do this term. This is easy. N1 cross N1 is 0. N2 cross N1 is negative N3. So we have ML x double dot cosine theta negative N3, negative, negative. So I have all negative N3. The whole vectorial equation is in the N3 direction, so I can get the final equation. I'm going to divide by ml squared. So theta double dot is negative g over L sine theta, negative x double dot over L cosine theta. Okay? And you can immediately see the reminiscent of the pendulum dynamics. Do you ever remember this? Theta double dot equal negative g over L sine theta, This is the pendulum equation, but the effect of the car acceleration, here it is, okay? Any question? Any question, please? Please do not let things slip from your hand. Please, if you have any question, please come up with it.
Where did the X come about?
This is given position,
The
given distance of the point B, X, T. Any question, please? Any question?
A little query.
Sure.
Generally we define the vertical axis as 3, but this time we define it 2, so this cross.
Not necessarily. Not necessarily. We usually define the vertical axis in 3. It's up to you how to define the but you need to stick to the first definition. I have N1, N2, and N3 out of the board. Now defining any other consequent system vertices, I need to make sure of or keep track of the 1, 2, 3 order. Okay. The very first definition, it's yours. Yes, please.
Last lecture you talked about coordinate systems are not Cartesian. Are we going to stick with Cartesian?
It's up to you. It's dependent on the problem. Sometimes Cartesian work perfectly. Sometimes polar work perfectly. It's dependent on the problem. Any question, please?